Andrew, you're Professor of Astrophysics Education and an astronomer.
That's right.
Can you tell me a little bit about your area of research and how you got interested in this field?
Okay, well, I've been interested in astronomy all my life, I suppose. When I was young, I used to watch Star Trek, Doctor Who on TV. I guess people still do. But that got me interested in space and things out there. And really, the whole thing has come full circle, because years ago, looking at those TV programs, you know, Kirk would beam down to a planet and wander around on this alien world. Back then, we didn't know that planets really did exist around other stars. But in the last 20 years, astronomers have actually discovered thousands of so-called exoplanets, planets around other stars. And the more we discover, you know, it's as though we're living in the Star Trek universe after all.
So you mentioned exoplanets specifically. Are those the kind of planets that we look for alien life?
Well, ultimately, I suppose that's where the subject will be going. The first exoplanet, the first planet round another star other than the Sun, was found 20 years ago. And in the past 20 years, we've now found thousands of them. As yet, I would say we haven't yet found one that's just like the Earth, but it's probably only a matter of time till we do. So, as an example of a project that we're involved with here at the Open University, about 10 years ago, we got involved with a project called Super WASP, WASP standing for Wide Angle Search for Planets. And what's super about it is that it's two installations, one in La Palma in the Canary Islands, one in Sutherland Observatory in South Africa, and each of those has 8 individual telescopes, little telescopes, on a single mount. Now, why it's so great for looking for planets around other stars is that each of these cameras, it's only about that big, really, that diameter, 11 centimeters or something. But each of those has a very wide field of view, so we can take images of the sky that are about 50 times the area of the full moon with each camera. And we've got 8 on each mount, and then we have, as I said, one in the north, one in the south. So we can take images of a large patch of sky. And how this was set up was literally just to take images of all the stars in all the sky all the time. And so over the past 10 years that Super WASP has been operating, we have measured the brightness of about 30 million stars. And all we do is measure the brightness of every star every night as often as we can. And then if you join together all those brightness measurements to make what we call a light curve, you can see how the brightness of every star varies. Well, so far so good. How does that help us find planets? Well, if a star has got a planet going round it, and if the orbit of that planet is aligned with us such that the planet passes in front of the star once per orbit, the planet will block a tiny bit of light. If you've got a Jupiter-sized planet going in front of a Sun-sized star, it will block 1% of the light. So the star will get 1% dimmer every time the planet goes round. So all you've got to do is look at all the stars all the time to see which ones are winking at us to tell us they've got planets going round them. So with that, with Super WASP, we found, I think the total's now well over 100 of these exoplanets, which is a good proportion of the ones that have been found. Now, that's all well and good, but what I'm actually interested in is something of a spin-off from all that. We found 100 planets in these 30 million stars, and there are probably lots more that we haven't yet found. But what we have is these light curves, these brightness measurements of 30 million stars. And for me, that's an exciting set of data that we can use to do lots of other science. And what I'm particularly interested in is variable stars. What do we mean by that? Well, we mean stars whose brightness varies with time. Now, at some level, every star is a variable star. Even the Sun, the brightness varies by a tiny amount. So depending on how accurately you can measure things, in fact, every star is variable. But there are, broadly speaking, 3 types of variability we can see in these Super WASP stars. First of all, we know that stars like our Sun have sunspots, little dark regions, and all stars rotate. That the Sun takes, what is it, 14 days, 28 days. I should really remember, shouldn't I? Anyway, the
Doesn't
sun
matter.
the sun rotates in some number of days, and the sunspots come round. Well, many stars have got really big star spots on them, and as they rotate, those star spots come into view and then disappear again. And as a result, the brightness of the star varies as that spot comes into view and disappears. So with superwasp, we see maybe 100,000 stars whose light varies because they've got big star spots and they're rotating, and we see the brightness varying as they rotate. So we call that rotational modulation of the light. That's one sort of variable star.
Just out of interest, how do you know when it's a star spot or a planet, an exoplanet?
That's a very good question. If you've got a planet passing in front, you get a very characteristic change in the light. Because the planet is so small and it passes across the sort of the face of the star, you get a sort of U-shaped dip as the planet passes onto the edge of the star, moves across, and then passes off again. You get a very characteristic U-shaped dip. If it's just a big star spot and the star's rotating, you get a much more smooth variation with time, so you can distinguish them that way. But there are other sorts of variability too. We know that some stars pulsate. Literally, they get bigger and smaller on a sort of regular timescale like that.
Are those the ones that are called pulsars?
Not quite. In fact, pulsars were actually misnamed. Pulsars are rotating neutron stars. That's a whole other talk. Maybe I'll come back to that later. But pulsating stars, they pulse in and out. There's certain stars that have they're at a certain stage of their life where they have a particular mass and temperature, and they become unstable and they pulse in and out like that. And as they do, they get brighter and fainter and brighter and fainter. And again, they have a very characteristic pattern of variation. They tend to brighten very rapidly and then fade away on a bit of a longer time scale. And that maybe takes a day, a couple of days or so. But again, we see maybe 10,000 of those pulsating stars with superwasp. The type that I'm particularly interested in at the moment is yet another type of variability, and this is where we've got two stars orbiting each other. We call it a binary star. And again, if we're looking at the orbit edge on, so the two stars pass in front of each other, then every orbit, star number one passes in front of star number two, and then number two passes in front of number one, if you like. So we get, again, a very characteristic pattern of variation with so-called eclipses as the stars go round. And again, there's about 10,000 of those that we've seen with superwasp. So that work I did with superwasp, identifying these variable stars, has actually fed directly into some of our teaching. One of the first things I did a couple of years after we started with superwasp was identify a set of variable stars which were also in another star catalogue as X-ray emitting sources. So we didn't know what they were, but if they were emitting X-rays, they were probably some sort of highly energetic star. So I published a scientific paper that listed this catalogue of new stars we'd found with superwasp, variable stars that were also X-ray emitters, and there are about 360 of them. Now, we use that paper that I wrote as the starting point for a project for our students in our Level 3 astrophysics course. If the students choose this particular project, what they do is select one or more of the stars from that catalogue that I produced, and the students themselves observe that star using a telescope called Pirate, which is a bit like this one here, except that it's situated at an observatory in Mallorca, and it's entirely robotically controlled. So the Pirate telescope, the students control over the internet via the web. They point it at the target they want, they acquire the data, they download it, and they go away and analyse it.
So whereas here we'd use this control to move the telescope, they can effectively do that with a mouse? Exactly so, just from their home computer, wherever they happen to be. They work in groups. We have groups of students controlling the Pirate telescope, and they're in this project course, they're allocated so many nights of use. Hopefully they get some clear nights. They can observe the target they want, download the data, and then they produce a project report as a result. So they can swing the telescope round and up to look at their bit of the sky where their special star is. That's fantastic. Exactly so, yeah. Well, also, there are some OU students who've done this project in the last few years who've got such
great data, great results from their own observations. Outside of the OU module, they've written that up as a scientific paper themselves and had it published in an astronomy journal.
That sounds like a fantastic project. Andrew, thank you.
Thank you.